Now that we've seen Newton's law for universal gravity, we move on to our next concept, and that's the concept of potential energy. We saw before when we were looking at uh, our normal near the Earth's surface physics, we were talking about potential energy be equal to mgh, and we really cared about the change of the potential energy, so it was mg delta h. However, we know that this height, that if we change the height, the further away we are from the Earth, the less that gravity from the Earth actually pulls on us. So gravity decreases as we get further away, or there's two objects away, the gravitational attraction, or the force between them, gets less and less, which means that we would expect that this equation would no longer be true if our distances, our changes are large. So we actually have to go back to Newton's law for universal gravity to derive the right formula. And we can do this. This is easy to go through. If you have to know a little bit of calculus to go through it. But really all you do is you just apply the work energy theorem to Newton's law for universal gravity, that gmm over r squared. We just apply it and the equation shows up. We're not going to do it. Why? Well, you guys probably don't care too much about the actual derivation of this. However, what actually comes out of it is important, and this is something that you guys are going to be expected to know. So we have that the potential energy due to gravity between two objects, so the potential energy is given by gm1 m2 over r. Very similar equation to Newton's law for universal gravity, except for you'll notice that this function right here, this r, is not squared. It's just to the first power. And there is no vector quantities associated with this. We do keep the minus sign, however, we go to a scalar quantity. So let's look a little bit into this equation and see what it actually tells us. So again, r is the distance between the two objects, and it's going from the object doing the pulling to the object that's being pulled. Normally m1 is your object of interest. This is what's being pulled or what you're calculating the energy of. m2 is normally the object that's doing the pulling, such as the Earth. But the distance is from m2 to m1 in the way that I've just described it. There is this minus sign in here. So if we look at this equation and start to go through, and knowing that m1 and m2 are the masses that we've used before, if we look at this distance, the further these two objects go apart, the larger this number becomes. And if this number becomes larger and larger and larger, this quantity gets closer and closer to 0. Which means if we put in an infinitely far separation between these two objects, that we would expect our gravitational energy to be 0. Since r is going to be a positive value, it might have a direction, but it is just the magnitude here. Since r is a positive value, our gravity is always going to be a negative value. So at infinite far distances apart, these two objects have 0 potential energy. They're not interacting with each other when they're really, really, really far away. However, when they get closer and closer together, they start getting more interaction. The potential energy, because they want to be attracted to each other, the potential energy decreases, so it gets more and more negative, but the magnitude gets larger and larger and larger. So this mgh is no longer valid for us. We have to actually go to a new one, gmm over r. So we still have this, these two masses showing up. We still have that value of g. We could work through the same details again to show that this equation works near the Earth's surface, but it's just something that we have to do. So this is our more general equation of it, and we apply it really the same way we applied Newton's universal gravitational force. And again, g, just so you see it one more time, g is a small number, 6.673 times 10 to the minus 11 meter cubes per kilogram per second squared. And this is really all that we do to calculate the potential energy between two objects separated by a distance, each having its own individual mass.